right, so I'm here for you to explain this experiment of the how to find the velocity of a water using a Pitot tube. So just before I take you to the uh, experiment part, just one or two small things about Pitot tube which I thought I should share with you. And that is, it's a common device. It's a device used to measure the flow velocity. Okay, so that shows that it is not limited to only liquid or water. It can be used to measure the speed and pressure of air, liquid, or any gas, okay, for that matter. It is used very widely in aircrafts, okay, and many other very important or very places where things are very sensitive. It is used. You can Google it out more and check it out. Okay, so I'll quickly move to the experiment. I will not go too much into the theory part. Maybe you have learnt about it in your uh, lectures, so I will not mix up all that. So I'll just focus mainly on the experiment part. Fine. So now aim of the experiment is to measure the velocity of the flow of liquid, and the liquid that we are going to use is water, a simple tap water, okay, and using the Pitot tube because this experiment is Pitot tube. And apparatus, nothing much, just the setup that we require. Okay, I will show what is the setup. And a stopwatch. Okay, for a small part we require even a stopwatch. Now the specifications of the setup that we are using is that it has a pump, water pump, that will pump the water into the pipes. Okay, and that pump is 0.5 horsepower with 2880 rpm, rotations per minute. Okay, but now this specification you are not using anywhere in your calculation, but it is nice for you to know what kind of a pump we are using. Next, supply pipe diameter. Okay, the diameter of the pipe through which the water will enter where the Pitot tube is fitted. Okay, so that diameter is 0.044 mm. So divided by 2, you'll get the radius, and of course you can find the area of cross section, which is pi r square. Okay, so you can just try it, put pi r square, use the pi r square formula and check whether it is 1.52 into 10 raised to minus 3 meter square or no. Please check. Next, we have a manometer. I will show you the manometer. The length of the manometer is around 300 mm, and we have a measuring tank below in the setup. I will show you, don't worry. And the dimensions of that measuring tank is 335 mm. We are going to use the units meters, but I'm just giving you the factory specifications. So it is 335 mm, 330 mm by 390 mm in height. Okay, and these are the important formulas for you. All right, so actual discharge, from where this 0.335 has come, it has come from here. This is in mm. We are written this in meters. 330 is written as 0.33 meters, and 0.1, I will tell you what it is. In the experiment, we will be finding the height in the manometer. Okay, and the second part after finding the height is to find the rise time. You can see there's a time t here. Okay, the rise time, how much time it takes for the water to rise by 10 centimeter, very specifically 10 centimeter. And that 10 centimeter in terms of meter is written as 0.1. Okay, that's what is written is 0.1. So this is from the tank. This is from the, again, the tank dimensions. Okay, these two tank dimensions, and the height is 10 centimeter of water, and how much time t it takes to get this time 10 centimeter, that is 0.1 meter. Okay, we are not filling the tank to 390 mm. We are not filling the tank to 0.39 mm. We are filling the tank up to 0.1, okay, meters. All right, so that's your one of the formula. Then we have actual velocity, which is nothing but the actual discharge, that is qa, divided by the cross-sectional area. Okay, so this is the qa that you are going to find. You are going to simply divide it by the area of cross-section, and you are going to get the actual velocity. Fine. All right, then you also have the theoretical velocity, which is a square root of 2 times acceleration due to gravity g, which will be 9.8 meters per second square, because we are dealing in meters, so we will use 9.8 meters per second square. and the height difference in the manometer. Okay, next, the coefficient of the velocity will be this actual velocity VA divided by the theoretical velocity VTH. So this is very simple experiment with very simple formulas. So let's look at the setup first. This is the setup. All right, what all it has. It has a manometer. Okay, let me, maybe I can zoom it for you to show you the manometer. Perfect. So you can see this is the manometer. As I was saying, it is a 300 mm in height manometer. Okay, and you will be getting the height difference. Some water level on this pipe and some water level on this pipe. You will be subtracting that, and that will be your height difference. That is H. Okay, and we have this. This will be will help you to determine the Pitot tube height. Okay, this will help you to determine the Pitot tube height. All right, next we have the pipe of whose diameter was given. Okay, 0.044 mm diameter, and this silver, the pipe is quite dirty because of the soiled water that has entered in. But if you can see this steel thing, that is the Pitot tube. Okay, so if you can see the steel pipe here, that is the Pitot tube. Fine. Okay, that is the Pitot tube. All right. So if I can just erase everything, then I think you can see the silver thing, silver kind metal thing inside the pipe. That is the Pitot tube. Fine. And next, of course, this is the measuring tank of whose the dimensions were given. And as I was saying, okay, let me just zoom this for you. The time required to rise in 10 centimeter, anywhere you can start measuring anywhere, but 10 centimeter rise. Okay, so say if this is 30, so up to 130 mm, so that is 10 centimeter rise. What is the time it requires to rise in this tank? That time we have to make. All right, so that's it, nothing much to explain in this experiment. Let's go straight to the laboratory and perform this experiment and come with our data for calculations. Okay, so see you after the experiment for calculations. All right, so let's go and perform the experiment. All right, so what we will do is now start with this experiment on Pitot's tube. Basics about Pitot's tube is already explained to you before this. So now what we are going to do is start with an experiment. We will take around 5 readings at a distance of 0.5 every time. Okay, the setup has been shown to you, and I will not show you in the full setup in the video because of the resolution limits, but in the screen you can see what is actually required. That is one, the manometer readings you'll be able to see clearly, and you'll be able to see the readings of the scale here, where you will be able to go 0.5 readings every time up and down. Okay, so actually it is like we take 0 and then we go a centimeter above and a centimeter below, but what we will do, just to avoid the error and the confusion, we will take 5 readings in one direction downwards. Okay, fine. All right, so let's begin. So for that, what I'll do is I'll put on the pump. There may be a little noise in the video as I put on the pump, so you see that I hope my voice is audible after that. Okay, so I'll just put it on and the water will flow in. Okay, and we should take care that there is no water bubble. So initially I will do little settings to avoid the water bubble and to see that we get a very clean reading. Fine, so let me put on the motor to pump the water in. So I've done the adjustments, and I hope you can see in the camera also that the water level is quite stable now, and you can see the two reading, the lower reading and the upper reading in the manometer. Also, you can see the scale. I have adjusted the scale to around 2.5. So the first reading will be at 2.5. Okay, so the lower reading is around 43. This is at around 43. So I note it down at 43. And the upper one is around 154. So reading at 154. Okay, so apart from that, we will need the time that is required for the rise in water in the measuring tank for every 10 centimeter rise. How much is the time it requires? And for that, we will require a stopwatch I cannot put cameras on so many places to show you, but I can just take this reading for you. The rise in time required for rise in 10 centimeter in the measuring tank. Okay, so for that, what I need to do is I need to stop the outlet of the measuring tank so that water starts getting collected, and this water that is collected, okay, will lead to the rise in water by 10 centimeter, and I need to measure the time in my stopwatch. So I will do that for you, and cannot measure all this on your camera. All right, but the two important readings for you is available on the camera, so I'll do that for you. So I keep my stopwatch ready. I close the measuring tank. And then I'm ready. Alright, I stop my stopwatch, and as I stop my stopwatch, at the same time I also see that the outlet is opened up, otherwise the water from the measuring tank will flow out. So the time that I got is 8 seconds, 9 seconds, no, it's 8 seconds. So I write the time as 8 seconds. Okay. So next what we do is very simple. This is a very simple experiment to do. So what we do is I go down by another 0.5. So in your screen also you can see now I'm at 2 instead of 2.2, I'm at 2. So I take the reading now. The reading in the manometer also should change with it, and I see that the height is, the lower height is gone down to 37. So I know down 37, and this is 2, okay, 37, and the upper one is gone up to 155. All right, 155. You can see that you can take the lower meniscus, not even 155, 154. Okay, surprisingly the upper measuring tank has not changed much, but the lower one has. Okay, again I take the reading for the time that is required for the rise in 10 centimeter. All right, so again for that I close the outlet of the tank, and I am ready to take my readings. All right, so I'm done. This time I got 8 seconds. Again, same reading I got for time. And then, well, we repeat the same procedure for another 3 readings, okay, where I go down again to 1.5, 2 is already done. So we go to 1.5. So we're down to 1.5. You can see that in your computer screen. Okay, and that will lead to change in the manometer reading also. So the lower reading is now at around 34, 35. So I'm maybe down at 34 at 1.5. And the upper one is at around 150. And again, I take the time that is required for the rise in water level for around 10 seconds. So let's shut it down. Okay, I'm ready. Okay, so I'm done, and I got the reading 10 seconds this time. So last 2 readings now. All right. Again, we'll go down to the next one. Still go over to 1. And now we take the reading again. The lower scale is come to around surprisingly it's gone very up, and it is still going up. Let's take the reading, no problem. It's around 85. And the upper one has come down to 145. And again we take the time We note down the time again. Okay, so this time I got 7. So remember to open the tank. And finally we take the last reading that we take now. Alright, so let's put it down again. Alright, so for the last reading, we have the lower one at, it is still unstable. Let's wait for it to become stable. We got the last one at around 75. Not even 75, little higher, 77. Let's note it down. And the upper one is at around 128. And we just take the time required for the rise in water for 10 seconds, 10 centimeters. I'm ready. Okay, again I got 8 seconds. I note it down, 8 seconds. So that's it. So this is a very simple experiment that we are done with. Okay, so now let's do the calculations from the readings that we have got for this experiment. All right, so see you for the calculation part. Okay. So we are back with our data. Let's see what we got. If you remember, all right, I have tabulated it already. The readings were taken from 2.5 up to 0.5. So it was like the middle one could be treated as 0 mm and 5 mm, 10 mm above, 5 mm, 10 mm below. All right. These were the heights that we got. We got 43, 37, 34, 85, 77. All these is written in terms of meters. When we measured it using the manometer, we got it in terms of mm. Now we have converted in terms of meter, and that's why these extra zeros you can see here. All right. And of course, this is the other reading of the height too. Okay, fine. All right. So moving on, we can just subtract the two readings. Just subtract the two readings. Okay, just subtract the two readings and you will get the difference of the height in terms of meter. And these were the times that we had calculated for the rise in 10 centimeter in the measuring tank. All right. So using each of these formulas, so this QA, calculating QA is very simple. Just calculate 0.335, 0.33, 0.1. Okay, and then divide every time by the time that you have found already, and note it down or write it down in the QA column. Okay, and then divide the QA by the surface area. Okay, that is 1.52 into 10 raised to minus 3. Each of the values, you will get these values, and this is the theoretical value. Be very careful. G we are using equal to 9.8 meters per second square. So see that you use this to get the theoretical value. Okay, now if we have performed experiment very well, then we should have got both these readings almost same, but you can see there is some kind of error. Okay, this is almost 1, this is 1.4, this is also 1, this is 1.5. This is quite a huge difference, almost 2 times. Okay, these ones are come little proper, this is also come little proper. So these 3 readings are come proper, but the first 2 readings have gone little bit off. Okay, and on an average, if you take an average, the mean, you find this is 0.9 and this is 1.3. Okay, not so bad. All right, not so bad, but it should have been little proper. So if you find the coefficient of velocity, that is CV is equal to VA by VTH, this is VTH. Okay, if you find the coefficient, if you divide this mean value, this value by this value, if you divide the two values by each other, you get 0.68. If you get 1, then means you have done experiment perfectly. Okay, if you get 1 or very close to 1, it means you have done experiment perfectly. Now 0.68 means we have almost as much as 32% of error in the readings that we took. Okay, almost 32% of error is what we have got in this readings. Okay, so that could, many reasons could be there. The water is not so clean, and also maybe we have used it after many days, so maybe it requires some cleaning. But at least out of 5, the 3 readings are quite good. Like if I take an average of these and these, then I'm sure it would agree quite a lot between each other. Okay, so error has come, a huge error has come because of these 2 readings. Okay, anyways, so if you plot a graph, because of our errors, we find these red ones. This red one is the actual velocity, and the blue one is the theoretical velocity. You can find them, it is quite scattered. Okay, it is quite scattered. All right, so what we could do is just draw a line in between, taking the majority point and just draw a line on an average. Otherwise you'll get a very zigzag line. Fine. All right, look at the graph. We have velocity of fluid on the y-axis, Pitot's position on the x-axis, and these are the units. So your graph, when you plot on the graph book, should also be as it is shown here. Okay, of course you need not show this color one. This is shown so that you understand which one is. So what you could do is, on top of the graph you can write like this is a actual, so you can write actual velocity. All right, and on this you can write theoretical velocity in your graph book. Okay, theoretical velocity. All right, theoretical velocity. Fine, so that's a graph. And finally the results, we got 32% of error, but we can say that the measurements of the theoretical and actual velocity along the diameter of the tube are in close agreement. Okay, and next, the coefficient of velocity is found to be 0.68. Remember, you should get it very close to 1. Okay, something like 0.9 and above, or at least 0.85 and above. Fine. All right, so with this we finish the experiment, and I hope you enjoyed it. So okay, maybe we meet for some other experiments online. Thank you.